Good morning, I'm Ethan Shapera. I'll be talking about high throughput search for new plasmonic materials. This is work I've done in the group of Andre Schleifer at the University of Illinois at Urbana-Champaign. So, a brief outline. I'll start off with an introduction to the project, some brief theoretical background on plasmonics and machine learning. Then, in methods, I'll talk about density functional theory and model validation. Then I'll present some preliminary results and finish with some future work. So, first off, what is plasmonics? With plasmonics, the goal is to control light at a sub-wavelength scale by exciting collective oscillations on a metal dielectric interface. These oscillations can be either propagating as surface plasmon polaritons, that's shown in the upper figure here, where we have an extended metal dielectric interface, and the electrons will oscillate back and forth across that. Or they can be localized on nanoparticles as localized surface plasmon resonance, LSPR. So with that, we have a sub-wavelength scale nanostructure, and the electrons are confined to oscillate only on the surface of that structure. So plasmonics would allow numerous applications, including sub-wavelength waveguides, nanoantennas, superlenses, sub-wavelength imaging, nanocircuitry, and biosensors. So as an example, here's a proposed biosensor where in white we have a gold nanostructure on top of vanadium dioxide thin film, and by measuring the absorption and transmission of the structure, we can tell what biomolecules are present in the area. So here's a demonstration of what plasmons actually look like. This white outlined box is a 500 nanometer long gold bar, and colors here represent the magnitude of an electric field. So right now with this deep blue, the electric field is 0, but we're going to apply an electric field and it will become red, indicating a larger magnitude. So let's see if this works. So here is an incident initial pulse of light being applied to the gold bar. It will proceed for a little while. Yep, and here the light has stopped, but we still have even after the light is no longer applied, we still have oscillations of the electrons on the surface of this gold bar. These oscillations are the plasmon resonance. In this case, since they're localized, they're LSPRs. So the response to an applied optical field in this scale depends both on the material choice and the geometry. Currently, there are quite a few possible materials used. So for instance, there are noble metals, gold, silver, copper, which are good because they have high conductivity, but they suffer from large visible losses from interband transitions. So while they could work well at IR frequencies, they're not as good in optical. Another choice is doped semiconductors. In these, you can tune the band gap in order to prevent interband transitions, but they can require high doping concentrations, which may make them unstable. So in this figure, there are three quantities shown. On the vertical axis, interband losses. On the axis coming out, carrier concentration, and along the page, carrier mobility. Ideally, for a plasmonic material, you want a high carrier mobility and low interband losses so that the plasmonic oscillation can continue for a long amount of time, and carrier concentration you would tune based on the particular application of interest. So two general criteria we can use in choosing plasmonic materials. First off, we need low interband and intraband losses in the optical portion of the spectrum, and also we need a negative real part of the dielectric function in order for the modes to propagate. So changing gears a little, machine learning. With machine learning, the goal is to automate pattern detection in large data sets. So generally, these problems consist of having some descriptors, which are quantities which we can easily find, and some target values, quantities of interest. But the trouble is we have limited knowledge of how to connect the descriptors to the target value. There's something missing, or at least no efficient method for relating them. So with this, we provide a large training set, systems for which both the descriptor values and target values are known, and then we iteratively search for the best statistical relationship between them. So in this project, the goal is to find new materials for plasmonics at optical frequencies. There already are databases of materials such as Materials Projects or ICSD or OQMD, which contain tens to hundreds of thousands of materials, but it's not computationally feasible to calculate all those dielectric functions. So what we do is we build on existing databases by carrying out DFT on a subset to form a training set. We then machine learn these plasmonic figure of merit values called quality factors, then apply the learned models to find new candidate materials, and we use this as motivation to better understand the physics underlying ground and excited state properties. So dielectric function tells us the response of a material to an applied electric field. Physics described by the dielectric function depends on the energy of interest. Within the optical range, the properties are the electronic band structure, so the energy momentum relations of the electrons. The dielectric function has contributions due to both intraband transitions, which I show in this green arrow near the Fermi level, in which electrons will oscillate by small amounts, and also interband transitions, shown by the purple arrow in the upper figure, in which an electron is kicked by a photon from a filled valence state to an empty conduction state. So to model these, we use a Drude model for the intraband contribution, and density functional theory we would find the interband contribution. So for plasmonics, we have a locally enhanced electric field near the interface. From that, we can define a quality factor, Q, which equals the enhanced electric field over the incident electric field. The loss for a plasmonic material is then due to the imaginary part of a dielectric function. When we solve Maxwell's equations near the metal dielectric interfaces, we can get quality factors for both LSPRs and SPPs. So LSPR minus epsilon 1, the real part, over epsilon 2, the imaginary part. For SPP, epsilon 1 squared over epsilon 2. And in this project, we'll consider the quality factors at 3 energies: 1.1655 electron volts, the operating energy of a neodymium YAG laser; 1.9595 electron volts, the energy of a helium neon laser; and 2.8075 electron volts, the energy of a helium cadmium metal vapor laser. So the purpose is to predict quality factors of materials using descriptors obtainable only from the chemical formulas, such as average atomic mass, number of electrons, etc. And this will also tell us how atomic properties influence the bulk properties. There are numerous algorithms available. In this work so far, we've found that adaptive boosted decision trees work particularly well, and we employ the machine learning Python library scikit-learn. So work is also underway to develop an automated machine learning system which will completely automate the process of machine learning for this type of work and will be released on completion. So the general workflow for this is we'll start off with some arbitrary chemical formula, AX, B, Y, C, Z. Then we predict its metallicity, whether it's a metal or a non-metal, because those have to be treated separately. For metals, we then calculate the dielectric function and omega p. From VASP, we machine learn the quality factors, and then we'll perform DFT on high Q class of materials. Non-metals, overall similar, but in this case, we also have to find the energy gap, and the plasma frequency is now dependent on the doping concentration. But once we have that, then we can machine learn quality factors and do DFT in much the same method. So the DFT tells us the contribution to dielectric function from interband transitions. We construct training sets as approximately 1,000 randomly chosen metals from Materials Project. We use a PBE exchange correlation functionals with a plane wave cutoff of 550 electron volts, which have all been found to be sufficiently converged. So our DFT is performed with VASP on the Blue Waters computer. Now, since we're interested in properties that occur right at the Fermi level, that means we have to have a very dense K-point sampling. So what we found is with a 25 cubed gamma center mesh, omega p, the plasma frequency is typically converged within about 4%, but to be safe, we'll use a 31 cubed gamma center mesh, which is found to be sufficiently converged using the tetrahedron integration method. So for model validation, machine learning is very susceptible to the problem of overfitting. So say you have n data points, each with a different x value, then you can perfectly fit an n-1 degree polynomial to that, but that does not mean that that polynomial is the one which will best generalize it. So you have to look at balancing how well does the model fit the data correctly versus how well will it generalize to new data that is added. So to do this, we use an 80-10-10 validation set. The way that works is we randomly select 10% of the training data to be part of a testing set. This is left fixed. Then we perform numerous iterations in which 80% of the data is used to fit the model and 10% is used to validate the model. This allows us to test that the models found are not too dependent on the training set, and it allows us to balance the size of a tree or a network versus the fitting, validation, and testing errors. So for our first results, we check our training set to see if there are any possible high quality factor plasmonics that we just stumbled on accidentally. First, we see some metals already in use, so gold, silver, aluminum, which have quality factors all right around 1. Then we find magnesium and gallium, which are less commonly used plasmonic materials, but they do appear in experimental literature, and both also have relatively high quality factors. And here we see two possible new plasmonic materials, copper, 3 gold, and silver tellurium. Both of these have higher quality factors than the 3 commonly used metals, and they have low energy above holes, so they may be stable. So in learning Q, we train decision trees for each quality factor. On the upper right is what these plots typically look like. We plot the machine learning prediction of the quality factor versus the VASP calculated quality factor. The red line is to guide the eye. Ideally, in a perfect model, all points would lie exactly on it. Black points are the testing set, the materials for which we leave 10% fixed, and blue is fitting the materials for which we fit the model, and green is our validation. What we get is mean absolute errors of 0.22 for fitting, 0.35 for validation, and 0.39 for testing. Within this range, it generally reproduces the trend, so higher quality factor plasmonic materials are predicted to have higher quality factors. Unfortunately, the error is on roughly the same order of magnitude as the typical values. If we look now at the distribution of the errors, so bottom figure here, the VASP calculated quality factor minus the machine learned quality factor, what we see is they have a roughly Gaussian distribution, so there's no one subset which provides particularly large errors. So if we apply the model we have so far to every metal in materials project, what we see are 2 possible new materials that are both stable and have high quality factors, so sodium lithium and sodium calcium. These also have the uncommon feature of a high quality factor even in the UV. So typically with metals, their UV quality factors will tend to decrease because they will have large amounts of transitions from valence to conduction states. So future work, in the short term, we're going to apply much of the same process to doped semiconductors, but this will also require band gap corrections due to the DFT error in gap for dielectric functions, and we'll also consider the amount of electron doping, which will be fixed at 1 value for the time being. Longer term, what the project will do is choose several high quality factor metals and doped semiconductors, and as well construct related compounds, then apply methods which can better capture correlation and quasi-particle effects, such as HSE or GW, and also look at the band structure and surfaces. The new physics we expect to learn is determining the suitability for plasmonic applications, and we hope to better capture the electron-electron interactions by including more physics, such as HSE correlations or spin-orbit coupling, and want to study the effect of surface versus bulk on optical properties. So why blue waters? First off, the large number of nodes allows submitting many DFT calculations simultaneously, which is vital for creating training sets in a timely manner. Accurate descriptions of excited states, such as using hybrid functionals or GWs, require expensive calculations, which can be done thanks to the power of blue waters. Surface calculations will require large supercells up to hundreds of atoms, which, once again, to run efficiently, we need to parallelize over many nodes. And we also have issues with data storage of the VASP output files. So, thank you.